Hello everyone and welcome to another video brought to you by DJI Enterprise. My name is Ron Lee from the Enterprise Solutions Engineering team, and in today's video and in few upcoming videos as well, I would like to spend some time walking through the photogrammetry workflow. We'll break down the process step by step, covering project preparation, mission planning, data acquisition, and data processing. So the goal of this video series is to help you get started and take full advantage of DJI's powerful reality capture and surveying drone solutions. Before we begin, I would like to give a special thank you to Jimmy Kenyon, who provided both the site access and the data used in this educational video series. His support made this workflow to walk through possible. Okay, so within today's video, I will be first talk about the preparation phase and mission planning phase. But before that, let's go through the hardware we used for this workflow. First, we used Matrice 4 Enterprise, that is our drone and camera. We're using the RTK3 mobile station, that is our first RTK base station for the drone. Secondly, that is also our rover station used to capture the GCP and checkpoints. On the software end, we're using the Pilot 2 application for the mission planning. And we were also using the FlightHub 2 software for mission planning. You can choose to use FlightHub 2 or Pilot 2. I will go through these two software in the video, just so you have a preference. So one is building to the remote controller. You do the mission planning on the remote controller. The other one is web-based. So you do the mission planning on a web browser. And FlightHub 2 also supports data processing. You can get the photos collected, upload them to FlightHub 2 for it to get processed. That's also something you can do, which overlapped with the functionality on the Terra side. But again, one is on the cloud, one is local, processed under your personal computer. In addition, we have Enterprise application, that is Android software bundled with the DRTK3, used as a data collector for collecting the ground control points or the checkpoints coordinates for validating and improving the accuracy of your project. Overall, let's step into the actual workflow. I have divided the four phases: preparation, mission planning, data acquisition, and data processing, based on their scenes. The idea is to maximize amount of work to be done under indoor scene, rather outdoor scene. We want to minimize amount of work when we're outdoor or when we're on site. That is the data acquisition stage. So that's why we have a preparation phase. We want to kind of shift all the work that could be done indoor away from outdoor. The first thing you can check is going to be the weather and the regulatory before you arrive on the site. Check to make sure the weather is suitable for the flight, and check to make sure the regulatory for the flight site is okay. If the airspace has regulations, make sure you have proper waiver or you file authorization ahead of time. If you're using untripped network or any sort of network connectivity to acquire map, for example, or anything, make sure you have internet connectivity. If you use the untripped service, make sure that untripped service have network reception at the area where you're flying. You can verify this by checking the baseline between your site location to the closest station under the untripped network. Next we have is to define the project boundary and the coordinate system. First, you want to make sure to define the project boundary. You can use a KML file, which can be generated from Google Earth, to load it into the mission planning software later on to create the mission planning. But you want to know that boundary ahead of time, preferably to have a KML file ready for mission planning. And the next one is going to be the coordinate system. You want to make sure you know what your deliverable is going to be in which coordinate system. So that target coordinate system is going to be the final deliverable you exported. If it's arbitrary, that's fine. We just need to know what kind of a coordinate system we're outputting our data into. So that is important because if we don't define the coordinate system properly, we'll not be able to align the drone captured data along with others. So if it's local coordinate system, DJI Terra software doing processing phase have a tool called 7-parameter transformation, can transfer that coordinate system from geographic to that custom coordinate system. But to be minded is when you're using the drone GNSS to collect the photos, that coordinates for each photo is embedded, that is in WGS84 coordinate system with ellipsoidal height unit in meter. That's something you need to make sure you know ahead of the time. But again, if you're only doing, for example, reality capture for a small scene, you just want to have the visual out, maybe exported the coordinate system in arbitrary, this could be something you can skip. The next one is hardware readiness. Make sure you have all the components, including the drone, camera, remote controller, base station, running the latest firmware by referencing to our release note. Usually, for example, if you're using P1 with the M400, you gotta make sure to check the M400 release note, make sure that firmware under the latest batch of the update match on that list. Similarly, if you're using 350 with your P1 sensor, go to the 350 website, check out the latest release note. Make sure that P1 firmware version match with what's shown on the list. Next, we want to make sure to pre-charge all the batteries. That includes the remote controller batteries, drone batteries, RTK batteries. Make sure you have enough batteries for completing the flight when you're on site. If you're working on a large-scale project, make sure you bring a generator or a DJI power station, for example, for providing continuous power and charge the battery as the drone flies, so you can rotate the battery back and forth doing the operation. You also want to make sure you have enough storage on the SD card. You want to make sure you use high-speed SD cards and memory cards for data capturing. So make sure you prepare that ahead of time. Under camera settings and application settings, there are a few things I recommend to do. First is to ensure that mechanical shutter options is enabled if you're using drones that has mechanical shutter like P1, M3E, M4E. Why do we need to enable mechanical shutter? This is just to reduce motion blur, and that makes you can fly faster without slowing down and capture sharp image. We also want to make sure to disable the lens dewarping. That way we can preserve the original photo and have that distortion later on to be corrected using Terra software or FlightHub 2 software. The next one is going to be the mission planning phase. So for this phase, we're actually doing the mission planning work, right? First of all, there are two ways for doing this. Like I mentioned, we have Pilot 2 software that is Android-based, preloaded on the controller. We have FlightHub 2. So let's talk about Pilot 2 first. First of all, during the preparation phase, we have collected the KML file exported from Google Earth. So in this specific case, I had the KML boundary file from Jimmy, and all I need to do is get that file loaded to the remote controller, whether through micro SD card or USB flash drive. I can show you how that process looks like. So over here, I'm under Google Earth. So just want to provide you a example on how to make a polygon in Google Earth and get the polygon exported as a KML to get the boundary file there. So under the Google Earth, you can select Add Path or Polygon tool there. select that one, and from here you just need to make sure to draw your polygon. That's our mapping area, for example, and we're going to select Save to Project. Okay, and there you go. Now you have a polygon under the content page or content list. Now to export this out, we just need to highlight this and make sure to select File and select Export as KML file and define the download directory. In this case, I have a USB flash drive inserted. I'm just going to download it directly into the USB flash drive and eject my USB flash drive afterwards to get that transferred to the remote controller. And I will show you how that process looks like. Okay, so now I have that KML file here in the USB flash drive. I just need to make sure to insert this into the remote controller. You can also use the micro SD card, or I guess more easier way for you to do is probably just connect the remote controller directly to the computer as a storage unit and just transfer the file that way. Well, because I'm using a screen mirroring tool, that doesn't allow me to do file transfer anymore. So I will have to do the USB flash drive way. So you want to make sure to open up Files and under Disk, that's our KML file. In order to import the KML file properly, you cannot import directly from the USB flash drive. You have to make a copy. So over here, I'm just gonna make a copy and select copy to, and I'm gonna select internal storage directory here. Maybe I'll put it under documents. There we go, copy. And copying one item, you can check the progress here. Now that's finished, okay. Now once that's finished, we can exit and open up Pilot 2 application. And we're gonna select flight route here. And upper right corner, we're gonna select add and import route. And from here, we wanna go to storage and 0, documents, and that's our KML. So we're gonna check the KML file here and select confirm to load our KML. For mapping area, we're gonna select area route here. Okay, and as you can see, that has been loaded, and which is default to P1. We're gonna change that. So click on this. As you can see, that boundary is there to work with, and we don't have to modify this boundary anymore. From here, what we're gonna do is we're gonna add a few things because it was default to P1. That was incorrect. So we're gonna expand this and select this icon to edit the mission. This is the mission planning parameters, and we're gonna make sure the name is right. And the first one is going to be the sensor selection. We're gonna change this from aircraft M300 RTK to Matrice 4 series, and we're gonna be using the Matrice 4 Enterprise, and select OK. Okay, so once we finish import the KML boundary into the Pilot 2 application, the next step is to set photogrammetry parameters. There are a few parameters you need to set. The first one is going to be terrain following. You don't have to enable terrain following if the mapping area is relatively flat in terms of elevation change, but if there's elevation changes like little hill or large amount of area you want to do mapping with, I would recommend to do terrain following, and that just keep the distance from the drone to the ground more even as it flies. Also, this helps avoid any obstacles that is on the horizon. So how to enable terrain following? There are currently 3 methods for doing this. The most easiest way is you download the digital elevation model directly from the Pilot 2 application. So under the Pilot 2 applications, you can select AGL or above ground level and select terrain following, and there's an option for you to download ASTER digital elevation model directly using the Pilot 2 app, and that digital elevation model was captured from the space shuttle. It has a resolution about 30 meters. Not perfect, but at least it's a reference you can use. If you want a drone to follow the terrain at a higher resolution model, that's the second method, which is the model import. You can import 3D model into the pilot application and call the model for terrain following. The third method is real-time terrain following. This feature is only available for terrain following supported drones like the Matrice 4 Enterprise, M400. These drones support real-time terrain following, and it is using the visual sensor on the bottom of the drone to detect that ground distance in real time and ascend and descend altitude correspondingly based on the real-time terrain. By using the real-time terrain following, it is not as accurate as using the digital surface model. However, this reduces the time for gathering that digital surface model or digital elevation model needed for terrain follow. The next option we have is going to be the ground sampling distance. And the GSD or ground sampling distance generally correlates with the resolution of your 2D or 3D model after it gets processed. Smaller GSD value would output much better in terms of the resolution, and higher GSD would output a model with less resolution. Also, the GSD is a good parameter to define the accuracy of the project. So based on the accuracy requirements of your project, generally we recommend to multiply that accuracy requirements by 1/3, and that should be the GSD value you should be using, if not less. So just giving out one example here. Generally speaking, if a project requires 3 centimeter accuracy, we will need to multiply that by 1/3, which is 1 centimeter ground sampling distance. And adjusting the ground sampling distance will automatically affect the flight altitude that is relative to the ground. So if your camera system can output more resolutions like P1, which outputs 45 megapixel, it is going to provide much lower ground sampling distance compared to other camera systems, for example, M3E, M4E, which outputs 20 megapixel at the same altitude. This is also taking the assumption that the field of view of the camera or the focal length of the cam is the same. So when you're using a system like P1, for example, you can change the field of view correspondingly to maintain the GSD by having the flight distance higher or lower, correspond to the lens you'll be using. Within DJI Pilot 2 software, when you adjust the ground sampling distance value, the above ground level flight altitude is also going to get changed automatically, so I would recommend to change the GSD instead of changing the flight height. If you are doing a mapping task under area with minimal flight height requirements, and you found the ground sampling distance is not going to satisfy the accuracy requirements, something you can do is change the lens to a longer focal length lens. This ensures the drones can fly and operate at a safe altitude while capturing data. Next one we have is the overlaps settings. So what is overlaps? These are the factors that would affect the area of overlaps between photos. In the Pilot 2 application, you would find 2 overlap settings. You will find front overlaps and side overlaps. And usually you would find 80% front and 70% side is optimal for most of the terrain surface. And this is under the assumption of non-terrain following. If you're using terrain following, this is something you can reduce slightly. If you're operating at an area that is relatively flat in terms of the elevation, you can significantly reduce that side overlaps from 70% to 30% or 20% even. Have more overlaps generally is good. However, if you set overlaps ratio too high, that's going to cause the flight to be significantly longer and capture a lot more data. And vice versa, for vegetation, high oblique structures like urban area with skyscrapers and complex terrain, increase the overlaps is generally a better approach. Again, this is under assumption of non-terrain follow. If you're doing terrain follow, you can kind of reduce the overlaps correspondingly. And there's another parameters I like to kind of talk about is the margin. In the Pilot 2, you can change the margin of your mission. Generally, I like to increase my margin by a few meters, so the raw data capture will sufficiently cover the region of interest I set for the deliverable output. But keep in mind, increase the margin would have your flight route exceed the boundary you set. Make sure you review the flight route ahead of time and make sure your airspace is clear and safe for the operation. The next one I'm going to talk about is the course angle. So in Pilot 2 application, you can adjust the course angle of your flight route. Now this changes the direction of your flight route as well as the heading of the flight route. I like to avoid unnecessary turns, so I would manually adjust the course angle, making sure I can find a optimal angle for my route. And sometimes if your boundary file is a little too complicated, the flight routes got automatically generated may begin from the middle toward two sides. Adjusting the course angle can also help avoid having the drone flying back and forth from two sides of the project. And the next one we have is to adjust the start waypoint of your mission. So let's say if you are doing a mapping for maybe a unfinished highway and it's going to be a linear mapping. In this case, you can set the start waypoint further away from you and slowly flying towards you as it's capturing data. When you want to capture the side of the structure, you want to use the oblique methods to capture additional photos with gimbal tilted. So that way you can capture more photos from the side of the scene and that outputs better results. And in the Pilot 2 application, you can enable oblique and capture the scene with 5 directions. Pilot 2 application is going to generate 5 different flight routes for you to execute, and you can filter out, let's say if you just want to capture oblique data from north to south direction as well as from south to north directions, you can just tap on the 2 oblique missions for the drone to execute. And also please be aware, when using the oblique missions, that flight route is also going to exceed your boundary. For latest DJI Enterprise product model like the M4E, M3E, as well as the P1, they support Smart Oblique. By toggling the Smart Oblique feature, the aircraft is going to move its gimbal while it's flying to reduce the number of flight paths needed. And the aircraft would automatically adjust the speed of the drone to capture photos at different orientations within the scene. Smart Oblique is great to capture the oblique data for the scene because it reduced operation time as well as the size of the raw data. And there's one more parameters I like to talk about that is called optimize elevation. By toggling the optimize elevation option, the Pilot 2 application is going to generate an additional flight route, which is a linear flight route toward the center of your boundary. While it's flying that line, it's going to pitch the angle slightly to capture some oblique photos. This helps improve the elevation accuracy of your model while it's being processed by Photogrammetry engine. So for general surveying purpose, I highly recommend to enable this option even when your deliverable is just going to be in 2D. Okay, so once you adjust these parameters, you're good to go and you can save this file into the remote controller. Okay, so after Pilot 2, let's talk about FlightHub 2. FlightHub 2 is a web-based software that has the capability for doing mission planning as well. I'm currently logged into our organization. When you first log into FlightHub 2, it's going to ask you to create a new organization. And under that organization, you can create multiple projects. And after you create that project, for example here, you can actually see there are multiple options on the left side. Now, we're going to cover the mission planning aspect of the operation. So we're going to be focusing on this one. It's called a flight route library. You want to select that icon there. And this would show all the missions you previously created. You can select this icon to create a new route. And you can select this icon to import flight route. You can also download the flight routes you created and archive them if you want to. You can also merge multiple missions together if you want to. We're going to select create flight route just to kind of walk you through what that process looks like. You would find many settings you have already seen under Pilot 2. So I'm not going to go through these features again, but I want to show you how that workflow looks like. Once I select create route, there are different flight routes options for me to select from. You can find detailed mapping routes. Now these missions were designed to create a very detailed 3D model by capturing a lot of photos, and these models later on can be used for various of applications. For example, a detailed building model can be used for virtual inspection without sending people to inspect exterior of the building. Forensic users may want to use the drone as a reality capture tool to quickly capture a scene that they can archive as evidence. We have made videos to go through these features. I highly recommend you to check out those if you're interested. For this video series, we'll be just covering general mapping. We'll be using the area route, and we're going to be selecting that same aircraft, the matrice for enterprise model, and then we're going to give our new flight route a name and select OK. That's going to create a new route. Once the flight route is created, something you notice that is a little different compared to the Pilot 2, that is the FlightHub 2 is asking you to set a reference takeoff point. Now this reference takeoff point is mainly used for DJI dock operations. If you want to create a mission for non-dock aircrafts to execute, you can set the takeoff point to estimated location. Next, we're going to draw our mapping area by drawing a polygon, just like this. And you want to click on the last waypoint to confirm. Now, once that area is created, FlightHub 2 is going to generate the flight route automatically. As you can see, it already generates my flight route. It's going to take off, hover, fly to the first waypoint, which is a start point here, and finish, and perform a elevation optimization flight route. So this is normal, except the default altitude is way too high. I'm going to reduce this to 150 feet. And as you can see, when I adjust these parameters, the flight trajectory gets updated, as well as estimated photo amount and flight duration. Since all these settings are, if not same, very close to the Pilot 2 application, I'm not going to go through these again. I do want to show some differences between the FlightHub 2 and Pilot 2 when it comes to mission planning. One advantage I found using the FlightHub 2 is that when I click and hold my mouse wheel, I can actually rotate my map and check out my flight route in 3D space. So when I have a large scale mapping task, especially for those terrain photo ones, I have a pretty good understanding of where the drone is heading to and whether there's a chance or risk for losing the signal. And of course, you can define the start point as well. That is under advanced settings by select route start point and click on the set route start point. You can select and modify the start point of your route. Just click on that little check to confirm, and it's going to update the flight route correspondingly. And of course, you can also enable real-time terrain follow by selecting real-time terrain follow. That's going to change the color of the flight route to purple. But by default, if you select AGL, FlightHub 2 is going to use the global elevation data automatically to adjust the flight altitude based on the global elevation data. Once you're finished setting your flight mission, select Save icon here and exit out. And the next step is simply go to Pilot 2 application and download the route we created before you get to the site. Under the Pilot 2 flight route library, there's a tag called Cloud. You can select on that tag to get to the list of all the flight routes stored on the FlightHub 2 cloud end. In addition, if you would like to do a terrain following flight by using a digital surface model, you can import digital surface model in FlightHub 2 as well. So you want to go to first, model library, and upper right corner, you'll find an option to import your 3D model. That model can be 2D digital surface model, 2D digital elevation model, or point cloud or mesh model. One thing to keep in mind is the model needs to be in WGS84 coordinate system and ellipsoidal height in order for correct terrain following. Okay, so once we have synchronized the mission to Pilot app, we're ready to go. And at this point, What I like to do additionally is to prepare the location of the ground control points. And of course, prepare your ground control points ahead of time, as well as equipment for shooting these points. The ground control point needs to be visible from the drone captured imagery. If you don't know where to start, a standard 2 feet by 2 feet black and white target should have a pretty good balance in terms of the size. You don't want your GCP to be too small when you're flying at a very high altitude. And you definitely want to avoid setting GCPs under canopies. And when it comes to the number of ground control points needed, that really depends on the size of the project. But generally, we recommend at least to have 5 ground control points, 4 distributed around the corner and 1 distributed in the middle. These ground control points can be used to enhance the global accuracy of your data, but in addition, it can also be used as checkpoints for validating your model accuracy. If you're using RTK or PPK methods, you can consider reduced number of GCPs, or simply just use these GCPs as checkpoints to validate your output accuracy. So with that being said, that's everything about preparation and mission planning. The next video, I'm going to talk about data acquisition and a few items you might want to keep eyes on during the data collection. I will see you in the next one.